This lecture is part of an online course on rings and modules and will be about polynomials. We'll start by just quickly reviewing polynomials over a field, usually denoted by k. And you recall that first of all this has a division with remainder algorithm. So we can divide one polynomial by another and get a remainder of smaller degree. This implies that it's a Euclidean domain, just as the integers are, and just as we saw for the integers, this implies that it's a principal ideal domain and has unique factorization, so it's a unique factorization domain. Another consequence of this is that any finitely generated module is a direct sum of cyclic modules. This is proved just as for the integers, so this is the analogue of the theorem that says any finitely generated abelian group is a sum of cyclic groups. A cyclic module just means one that's generated by one element, so it's of the form k of x modulo some ideal. We saw in a previous lecture that this implies the Jordan normal form for matrices over the complex numbers. So we're going to discuss the unique factorization domain property a bit. First of all, we'll just do an example. Over a finite field, we can actually find the irreducible polynomials by sort of copying the way we do it for the integers. So for the integers, we have the sieve of Eratosthenes. So you write out all the integers in order until you get bored, and you cross off that because it's 0, and you cross off that because it's a unit. And the first number you get is a prime, and then you cross off all multiples of 2. And then the next number on the list is a prime, and you cross off all multiples of 3. And the next number on the list is a prime, and you cross off all multiples of that, and so on. And you can do the same for polynomials over a finite field. So let's just find the first few polynomials over the field with 2 elements. So what we do is we write out all the polynomials over the field with 2 elements in order of their degree. So we get 0, 1, x, x plus 1, x squared plus 1, x squared plus x squared plus x plus 1, and so on. And now, just as before, we cross off the first 2 because that's 0 or a unit. And the next one is prime, so we cross off all multiples of that. And the next one on our list is prime, and we cross off all multiples of that. So we cross off that one, and the next one is prime, and so on. Actually, you can speed this up a bit. I'd like to get to degree 4 just to have 1 or 2 examples for later. So we notice that divisible by x says the constant term is equal to 0, and divisible by x plus 1 is the same as the sum of the coefficients is equal to 0. So what we should do is we should really write out polynomials with constant term 1 and the sum of the coefficients equal to 1. So if we start with degree 3, we get x cubed plus x plus 1, x cubed plus x squared plus 1, x to the 4 plus 1, x to the 4 plus x plus 1, we want the sum to be non-zero, x to the 4 plus x squared plus 1, x to the 4 plus x cubed plus 1, x to the 4 plus x cubed plus x squared plus x plus 1. Now we continue as before, so we know the first 2 on the list must be irreducible, so these are irreducible. Then we have to cross off all the multiples of the degree 2 polynomial, and the only multiple of the degree 2 polynomial we have of degree 4 is this one here, which is x squared plus x plus 1 squared. You can do this using the well-known, if you know, but this is beginning calculus students always think that a plus b squared is equal to a squared plus b squared, which is usually not true, of course, but is true if you're working over the field with two elements. So it's very easy to square things over the field with two elements. You just square all the terms. So we get 3 more irreducible polynomials of degree 4. And pretty obviously you can continue this process for as long as your patience holds out, but going above degree about 6 gets a bit tedious. Next we recall that if a polynomial has a root a, it's divisible by x minus a. And to do this, you recall we write f of x is equal to x minus a times g of x plus some constant. So we're just dividing f of x by g of x and getting a remainder. And now we just put x equals a, and we find that c is equal to 0, so f is equal to g of x times x minus a. Now, a useful consequence of this is that over a field, a polynomial of degree n has at most n roots. And we should just check this. So if a1 is a root, what we do is we put f of x equals x minus a1 times g of x. And now we notice that any root of f of x is a1 or a root of g. And you have to be a little bit careful here, because here we're using the fact that there are no 0 divisors. If there were 0 divisors, this bit would break down a bit. And then we just apply induction, so g has at most n minus 1 roots, because g has degree at most n minus 1, and so on. Now we've got to be a bit careful about this, because we do need to use the fact that our field K is commutative and has no 0 divisors. And in fact, polynomials can have more than n roots if you're working over something which is non-commutative or has 0 divisors. And this is a bit disconcerting, because you're so used to thinking that a polynomial of degree n has at most n roots that it takes a bit of getting used to the fact this isn't actually always true. So let's have a couple of examples. First of all, if you take the ring z modulo 8z, then the polynomial x squared minus 1 equals 0 has 4 roots, because 1, 3, 5 and 7 are all roots. And here the problem is this has 0 divisors, because 2 times 4 is equal to 0. So we really do need to use the fact there are no 0 divisors. Another example is if you take the ring of quaternions H, then x squared plus 1 has equals 0, has roots plus or minus I, plus or minus j, plus or minus k. So there seem to be 6 roots. In fact, it's got a lot more roots than that, because anything of the form b I plus cj plus dk with b squared plus c squared plus d squared equals 1 is also a root of this. So there's an entire 2-dimensional sphere of roots, which gives you an uncountable number of roots of this polynomial. So there's a useful application which says that z modulo pz, if you take the group of non-zero elements of this is cyclic. So in number theory, we say that it has a primitive root. A primitive root is just a term in number theory for a generator of this. It's called a primitive root because it's essentially all elements of this are roots of unity, because their p minus 1th power is 1, and saying it's primitive means it's exactly a p minus 1th root of unity. And the proof of this is we look at the field z modulo pz. Well, why is this a field? It's a field because p is prime. So this is going to fail for if you replace p by something that isn't a prime. So x to the n equals 1 has at most n roots for any positive integer n. So this just says that z over pz star has at most n elements of order dividing n for any integer n. And this implies it's cyclic. So there's a really neat way of doing this by using a clever counting argument due to Gauss, where you carefully count the number of elements of any given order. But there's a lazy way of doing it. The lazy proof is to just use the classification of finite abelian groups. And here you can see that if a finite abelian group is not cyclic, then you can easily see that there's at least some prime p for which there are at least p squared solutions to x to the p equals 1. This shows that z over pz star is cyclic. In fact, the same proof shows that if f is any finite field, then the group of non-zero elements is cyclic. More generally, if G is any finite subgroup of the non-zero elements of any field K, then G is cyclic. The proof is almost identical to the proof that z modulo p has a primitive root. As usual, there are counterexamples to this if f is not abelian or has zero divisors. For example, if we look at z over 8z star, this is not cyclic because it's got 4 elements, 1, 3, 5 and 7, all satisfy g squared equals 1, so it's actually a product of two groups of order 2. So we say that number 8 has no primitive roots, and if you go to a number theory course, they'll probably tell you in great detail exactly which integers do or don't have primitive roots. As you might guess, the quaternions also fail this. So the group of quaternions under multiplication has a subgroup consisting of elements plus or minus 1, plus or minus I, plus or minus j, plus or minus k, and this is order 8 and is not cyclic. It's in fact the quaternion group, it's not even abelian, and in fact the non-zero quaternions has quite a lot of rather interesting non-cyclic subgroups, such as the binary tetrahedron and the binary icosahedral group. So should have another warning here. This is another slight trap to fall into. If a polynomial of degree n vanishes at greater than n points, it is 0. So this is not what the warning about. This is just a useful fact about polynomials we quite often use. However, a polynomial can vanish at all elements of a field without being 0. And if you're confused by that, you've forgotten that the fields can be finite, because if you have a finite field, well, it can vanish at every element of the field, but it still might be identically 0. So, for example, if we take the polynomial x to the p minus x, it vanishes at all points of the field z modulo pz by Fermat's theorem. That's essentially the same as Fermat's theorem. So when you're talking about polynomials over a finite field, you have to be a little bit careful to distinguish between the polynomial being zero in the sense that all its coefficients are zero, or the polynomial being zero as a function, because it can be zero as a function without all its coefficients being zero. And this occasionally causes a bit of confusion. What we want to discuss next is polynomials over z of x, where z is the ring of integers. And we want to show that z of x is a unique factorization domain. Well, the easy way to prove that a ring is a unique factorization domain is to prove it's Euclidean or a principal ideal domain. So let's just note that z of x is not Euclidean or a principal ideal domain. And you can see it's not a principal ideal domain because let's look at the ideal I, which is the polynomials with zero constant term. And this, you can easily check this as not principal. It's not generated by a single element. It's generated by two elements, 2 and x, but there's no single polynomial which will generate, zero, should have said even constant term. It's zero constant term modulo 2. So the polynomials with even constant term is not principal, although it can be generated by two elements. So we want to show that it's still a unique factorization domain. Well, what we first recall that q of x, where q is the rational numbers, is a unique factorization domain because q is a field. And we want to kind of reduce z of x to q of x. Well, you have to be a little bit careful because if you take a polynomial like 6x plus 3, this is irreducible in q of x, but reducible in z of x, because in z of x you can write it as 3 times 2x plus 1. And over the rationals, this is just a unit, so it doesn't count as a non-trivial factorization, but over z of x, it does. So this turns out to be a major problem. You can have polynomials with whose coefficients have a constant factor, and this means that irreducible has different meaning in these two rings. So in order to prove that the polynomials over the integers have unique factorization, we need to deal with this problem. So what we do is we define the content of a polynomial in z of x to be the content of f is the greatest common divisor of the coefficients. So for instance, the content of 6x plus 3 is equal to 3. And an obvious property is that f of x over c of f is still in z of x, and the greatest common divisor of the coefficients is 1. And the key point in proving that integer polynomials have unique factorization is the fact that the content of f times the content of g is equal to the content of f times g. So first of all, it's obvious that the content of f times the content of g divides the content of f times g. Sort of completely trivial. If some number divides all coefficients of f and some other number divides all coefficients of g, then it's obvious their product divides all coefficients of this. So the problem is to show the other implication, and we can simplify this. We can replace f and g by f over c of f and g over c of g. So we can assume that the content of f is equal to the content of g is equal to 1, and we want to show under these assumptions that the content of f times g is equal to 1. So how do we do this? Well, we're going to show that the content of f times g equals 1 by showing that no prime divides it. So let's pick a prime, and here I'm going to pick a prime in z, so 2, 3, 5 and so on. And we know that the content of f is equal to 1, so let's write f of x is equal to a m x to the m plus a naught. And now the content of f is equal to 1, so the prime doesn't divide all its coefficients. So let's suppose that some of them are divisible by p. Let's go up to a I minus 1 and x to the I minus 1. So suppose these ones are not divisible by p, and suppose that ai is not divisible by p. And let's do the same for g of x. So we might write g of x is equal to bm bn x to the n plus aj plus x to the j plus a j minus 1 x to the j minus 1 plus, so these should be b's, plus b0. And again, we can assume that these ones are divisible by p, and this one is not divisible by p. And now if we multiply f of x times g of x, this is going to be some complicated mess. I mean, you know the formula for the product of two polynomials is long and messy. But let's look at the coefficient of x to the I plus j. Well, it will be x to the I plus j times a0 bi plus j plus a1 bi plus j minus 1 plus ai bj plus ai plus 1 b to the j minus 1 and so on. And now what we do is we look carefully at this and we see that all these ones are divisible by p. And that's because a0 up to I minus 1 are divisible by p. So that follows from this thing here. And on the other hand, all these things here also divisible by p because all the b's are divisible by p. And finally, we see that this is not divisible by p. And the reason it's not divisible by p is that, first of all, ai and bj are not divisible by p. And the second point is that p is prime. And here we recall that z is a unique factorization domain, so irreducible implies prime. So we're making use of this special property that irreducibles are prime, and we're using the fact that the integers z are a unique factorization domain. And I'm going to recall that a little bit later. Anyway, we now see that this is divisible by p, and this is divisible by p, and this is not. So this coefficient is not divisible by p. So the content of fg is equal to 1 because we've shown that for any prime in the integers, it can't divide all the coefficients of f times g. So the highest common factor of the coefficients must be 1. And now, from this, we can deduce that z is a unique factorization domain. So first of all, we should write down the irreducibles of z of x, and this is quite easy. There are two sorts of irreducible. First of all, irreducibles of z, so we get plus or minus 2, plus or minus 3, plus or minus 5, and so on. And the second type are polynomials of degree greater than 0 with content 1 that are irreducible in as polynomials over the rationals. And it's easy to check all elements of z of x are products of these irreducibles. And the problem we have to show is to show these are prime. in z of x. In other words, we've got to show that if f divides the product of two polynomials g of h, then f divides g or f divides h. And this follows from using, well, first of all, we need to use the fact that the ring of polynomials over Q is a unique factorization domain, so irreducibles are prime. And we also need to use the fact that the content of Fg is equal to the content of f times the content of g. So we're using this plus Q of x is a unique factorization domain. And now, for example, if we want to show that these irreducibles are prime, we just want to show that if p is a prime of the integers and p divides fg, then this implies p divides f or p divides g. And this follows immediately from this fact about the content. And we also want to show that if f divides g h, then f divides g or f divides h for f, an irreducible polynomial. And I'm just going to leave that as an exercise. It's slightly more complicated than this, but not very difficult. And again, you use these two facts here. So that shows that polynomials over the integers form a unique factorization domain. Well, we can do more than that. So similarly, if R is any unique factorization domain, then R of x is a unique factorization domain. And the proof is similar. We define the content of a polynomial, and we have to prove the content of f times the content of g is equal to the content of fg. And you recall that the proof of this for z of x used the fact that z is a unique factorization domain. And in fact, this turns out to be essentially the only fact about the integers we used in the proof. We just need to know it's a unique factorization domain. And the proof of this just goes through for any other unique factorization domain, and we can just copy the proof and see that polynomials over a unique factorization form a unique factorization domain. And the nice thing about this is we can repeat this. So if we've got a field K, then K is a unique factorization domain. This implies K of x is a unique factorization domain. And then we can repeat it again and deduce that K of xy is a unique factorization domain, because this is just polynomials over K. And we can keep going. We find that K of x1 to xn is a unique factorization domain. So polynomials in any number of variables over a field have unique factorization. If you want, you can push this even further. We can take polynomials in an infinite number of variables. Is still a unique factorization domain. And this is easy to reduce to the case of polynomials in a finite number of variables, because if you've got any polynomial in an infinite number of variables, it only involves a finite number of variables, and any factorization only uses those same finite number of variables. So the fact this is a unique factorization domain easily reduces to the case of polynomials in a finite number of variables. Similarly, if we take polynomials over the integers in any finite number of variables, then this still has unique factorization. And of course, you can take an infinite number of variables over the integers if you like. The next problem is to discuss algorithms for checking whether polynomials over the integers are irreducible, or to try and find an explicit factorization into irreducible polynomials. So this will be the topic of the next lecture.